So, welcome to today's NPTEL Live interactive session on geosynthetics and reinforced soil structures. Today, we will be solving some problems from the bilinear wedge, from the design of reinforced slopes using bilinear wedge, and then we will be uh, seeing how to for an embankment using uh, sorry, just a second.
Hello. So I hope that this audio is audible to you.
Yeah. So as I was saying that today we will be solving some problems from the one problem from using the Jewell's theory, where the bilinear wedge is used to design a reinforced slope using geogrid, and after that we will be seeing uh, how to design the reinforced foundation for an embankment situated over soft soil. All right. And after that, so as you might have seen that in this week, nothing much was taught. Right, means nothing more than this was taught. Only these two topics were taught. So I will be discussing one more important. I will be discussing one more uh, important part from geotextiles and geosynthetics, that is designed for reinforcement of unpaved road. Okay, so this is not a part of your syllabus. Yeah. So design of yeah. So as I was saying that we had solved some problems uh, regarding the design of reinforced walls. Then in the previous class, we solved some problems for reinforced slopes. And in today's class, today's interactive session also, in the beginning, we will be solving one problem where we'll be using the to Jewel's method to design a reinforced slope. Okay, using the bilinear wedge theory. After that, we will be seeing how to solve the problem wherein an is situated over a embankment is situated over uh, a soft soil foundation, and we will be using geocell to reinforce the foundation. All right. So only these two things were actually discussed in the class. And so I thought that so as we have time, right? As we have to spend 2 hours, so I thought that I will just introduce you to something uh, something known as the reinforcement of or the design of unpaved roads using geotextiles and geogrid. All right, so this hasn't been taught in the class, I guess. So I just thought that I will just show you how to do that. So all these details are actually available in a corner's book. So I thought that actually when I had done this course during my bachelor's, at that time I had studied that thing. All right. So I thought that I will just discuss as we have time. So I thought that it will be better just I just discuss this thing, and you should also know that how to design this road, unpaved pavement. Okay. So unpaved pavement, how in what way this geotextile or this geogrid is beneficial. Okay, that we will see in case of unpaved road. And what I mean by unpaved road, that also you will see. We will define that first. What do we mean by unpaved road? And then we will be seeing How we can use geotextile and geogrid in that case. All right. So let us start slowly. So Jewel's method, using Jewel's method, actually we had solved one problem in the previous class also, right? We've solved one problem in the previous class. In today's class also, we will be trying to solve one similar problem. So in Jewel's method, so it has been derived using the bilinear wedge theory, right? So we will be using Jewel's charts, Jewel's design charts to solve the problem. Right. So let us see the simple problem in front of us. So we plan to construct a soil embankment at a 70-degree slope angle with the horizontal, okay, 70-degree slope with the horizontal and 10-meter height. Okay, so the height of the embankment is 10 meter. To be reinforced with unidirectional geogrids with TLTDS, means the design tensile strength of the geogrid is 25 kilonewton per meter. The soil is granular with unit weight 90 kilonewton per meter cube, and the friction angle is 35 degrees. And it has no pore water pressure. Okay, that is the pore water pressure coefficient 0. The uniform surcharge of 25 kP is there at the top, and we need to determine the number, spacing, and length of individual geogrid layers. All right, so in short, we have to design this. We have to reinforce the embankment. Okay, so we have to design this embankment. Right. So let us see. So uh, if you can remember whatever was discussed in the previous class. So the first thing that we do. So here, see, we have a surcharge acting, right? So as some surcharge is acting, so what we will be doing is that we will be determining the equivalent height first. Okay. So let us see that. So we call it H dash. So equivalent height will be equal to our height of the embankment plus Q by gamma. That's the Q is the surcharge and gamma is the unit. So height is 11, 10 plus Q is 25. And what is our gamma? Gamma is 19, right? So how much will it be? Uh, let's get my calculator. So 10 plus 25 divided by 19. So it will be, sorry, 11.32 meters. All right, so we got our equivalent height. Now what we need to do, we need to get our lateral earth pressure coefficient. All right, so how can we get our lateral earth pressure coefficient? So for that, we will be making use of this chart given by design chart given by Jewel. So what is the slope angle? Our slope angle is 70, right? Our slope angle is how much? Our slope angle is 70. And what is the friction angle of the soil? The friction angle of the soil is 35, right? So let us just see. So approximately uh say 0.14. All right, approximately say 0.14. Approx. All right. Now using this, what we will do, we will determine the design lateral force. That is half gamma dash square into K. So half 19. What is H dash? square into 0.14. So how much will it be? Half into 19 into 11.32 square. 170.43 kilonewton per meter. All right. Now we will determine the minimum number of layers. To get the minimum number of layers, what we will do? See, we have the strength of design tensile strength of each grid, right? So we will, if we divide this design lateral force by this uh, design strength, we will get the minimum number of layers that we have to use to get a stable structure. All right. So minimum number of layers is equal to yes. So 170 is equal to so 7 layers. So minimum we need to have 7 layers. All right. Now the next step is to get the lengths of the reinforcement. So for that, we will be using these two charts. Okay, one is for the overall stability and one other is for the direct slide. Let us see for overall stability. So 70 degrees and this is for 35. So approximately say point how much? What should it take? Say let us take approximately 0.41. All right, so approximately let us take it as 0.41. So L by H dash overall is 0.41. And from this for direct sliding, we get this one. Approximately say 0.22 or 0.21. All right. Say 0.22 direct sliding. Now, if L L by H overall is greater than L by H direct sliding, we generally provide L by H overall length throughout the okay. We provide same length throughout. All right, we provide same length throughout. So we will be choosing this, right? 0.41. Margin. So what will be our length? Length will be 0.41 into how much? What is the H dash? 11.32. All right. So 0.41 into 11.32 is 4.64 meters. All right. So this much is the length that we have to give, provided the length of reinforcement that we need to give. Now the next step is to design this reinforcement, right? The spacing of the reinforcement. For that, what can we do? Let us just stop this. Share my screen. Yeah. Um, Yeah. All right. So total depth is how much? Depth is equal to 10 meters. Let us write 1 to up to 10. Then what is the vertical pressure? Vertical pressure is what? Vertical pressure is how much is our gamma? Gamma is 19, right? So 19 times depth plus the what? Plus the surcharge. So we'll get the vertical pressure. Let us just drag it down to get everything. So these are the vertical pressures. Now permissible spacing is equal to nothing but a TLTDS, that is a design strength, right? The design strength of the geogrid divided by Ka times the vertical pressure. Okay, so we have design strength is 25 divided by Ka is how much? Point how much? 14 times Ka times what is the vertical pressure? This much. So get this. This is the spacing. Now it is up to the designer. It's up to you to decide the spacing. All right. So now it is up to completely up to you to decide the spacing. So initially high spacing, so you can provide that. So what can we do? We can let us provide for all this. Let us provide spacing 1 meter. So generally we tend to provide little lesser spacing. Okay, a bit lesser spacing. So let us do it like that. Let us do it like that. I will just stop sharing. Just a second, I will share the screen. Yeah, just a second now. Right. So we got this. Right. We got this. So what can we do? Let us provide the first layer. So our embankment is the slope is something like this, right? Thing like this. So this is. So let us provide the first geogrid like this. At a depth of say 0.25. Okay, so like this, what we will be do, what we will start placing the geogrids. So from here, this one will be 1 meter. So like this, we will be spacing. So provide reinforcement at levels. So we'll just write the level, say 0.25 meter. First, we will provide, then 1 meter after that. So 1.25 meter, then 2.25 meter, then what? 3.25 meter, then 4.25 meter, then 5.25 meter, then 6.25 meter. Then let us write up to yeah, 6 point. Then after that, let us change it to 0.75. Let us change. So it will be 7 meter, then 7.75 meter, then 8.5 meter, 8.5 meter. Then let us provide it 9.25 meter, and lastly at 10 meter. Okay, lastly at this level 10 meters. So how many total? reinforcement are we providing? 1, 2, 3, 4, 5, 6, 7, 8, 10. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Right? So 12 layers we are providing. So what was the minimum requirement? How much was the minimum requirement? It was 7, right? Minimum we had to provide 7, but how much are we providing? 12. So this is greater than 7. So it's okay. All right. So we are providing 12 layers. It is fine. Now, so we have determined the so provide reinforcement levels at these levels, and reinforcement length is, what is the reinforcement length? Length 4.64 meters. All right. Now let us check for base sliding ones. Okay. So obviously it will satisfy because see, because we have chosen the length such that this is greater than this direct sliding length, right? So obviously this criteria will get satisfied. Check for base sliding. So let us just check this one once. What is the P that is coming? 170.43 kilonewton per meter. Right. What is the this resisting force? What is the resisting force? 0.8 into 1035 into 4.64 times height is 11.32 times 19 times 0.5 because we're averaging. So let us see 0.8 times 1035 times 279.51 kilometer per meter. So what is the factor of safety in sliding? 279.51. 1.64. Okay, is greater than 1.5. So, all right. So, like this, actually, we have to design using our jewels method. All right, using jewels method. In this way, we have to design. Now, let us come to the next thing, that is designing with geocell. All right. So just give me a minute. So as I was saying at the beginning that in this week actually very this only this duals method was taught and something some portion was discussed regarding this dual cell. The duals method only we already had solved one problem in the previous class only, and in this class we solved one similar problem again. All right. So now comes this geocell part. So I will be discussing little bit on this geocell and means on what concepts this thing actually came and who gave this thing. So we will be seeing that, and we will be seeing the problem that was actually given in the course and how to just going through it. That we'll try to understand that. See, all right. And after this, what we will be doing is that so we have a lot of time, right? Up to at least up to 8 o'clock, we have a time. So what I thought that we will have a lot of time remaining. So what I decided that there is one topic called reinforcement of unpaved roads. All right, reinforcement of unpaved roads using geogrids and geotextile. So that is actually not taught in the class. So I thought that just for your knowledge, I will just share that thing because when I had studied this course in my bachelor's, I had done that part. So I just thought that I will just share this with you just for your information. So that it might be beneficial to in the future. All right. Just it's just good to know things, right? So I will just share these things and how to solve those problems. We'll be just discussing that. All right. Now comes the part of designing with yourself. Correct. So, so GeoCell here we will be seeing how to reinforce the foundation soil. Reinforce the foundation soil that is made up of. See, we have a with very soft soil, okay, soft foundation soil, and that foundation soil we need to reinforce so that it can hold an embankment over it. So in order to strengthen the foundation, what we found strengthen that soft soil, what we do use GeoCell. All right. So uh, what does GeoCell do? GeoCell will actually prevent the lateral outward movements of the soil. So obviously, what will happen? Say uh, some things there, anything. Okay, soil is there. You provide no, so there will be tendency to move outwards. Right? There is a tendency to move outwards. So we will be preventing that movement using GeoCell. All right. So what happens? The geocell actually rotates the principal stresses and maximum shear stress reduction, and the failure surface is pushed deeper. So say the failure would have occurred like this. Okay. Now what happens? This failure surface is actually pushed deeper. Okay, so the failure actually doesn't happen. So here we have strong soil, right? And here is the soft soil, and here we have the strong soil. So what happens? The failure surface actually pushed deeper, right? So So we are actually strengthening. So we won't allow the failure to happen, right? Using GeoCell. Now, this design of GeoCell, there are many methods of this designing by GeoCell. So I will at the end I will suggest a paper. In that paper, actually, some methods have been suggested, summarized. So I will just suggest you to go through that paper. So it will be very beneficial to you. All right. Some methods are suggested. So one of the methods is designed based on the slip line method. And this method was given by Jenner, Bush, and Basil. Okay, in 1988. So quite old. Honestly. So if you ask me what is slip line method, so this is actually a little bit advanced topic. Okay, comes from the plastic equilibrium of soils. Okay, so this slip line method is a little bit advanced topic. This is also known as the method of stress characteristics. Okay, the slip line method. So in slip line method, what we do using more so just the basic in the very basic level, what we do is that so we try to construct the like try to get the equations of the failure subdivision, right? So we try to we actually get two families of equations from the by solving the differential equations that define the equilibrium of the soil mass and using the failure criteria from the mode this more stresses in those failure criteria, and using the from the failure criteria, and also from our uh, this limit analysis concepts, and then from our this what to say uh, this basic equilibrium equations of the soil. By solving all this, what we get two family of curves by solving. So those two family of curves actually represent the slip lines. All right, those family of curves actually represent the slip line. And using this is actually numerical technique. All right, this is actually a numerical technique which let us solve the problem. Okay, to let us helps us find the stress at any point. Okay, in a continuum, it helps to it helps, it facilitates us to determine the stress at any point. Okay, so this is a bit advanced topic, the slip line method. All right, so we won't be getting into the slip line method. All right, so for more details on how to draw these slip lines and all, I will suggest that you go through this paper, which is titled here Jenner Bush and Basin. They have just shown given the instruction on how they have not discussed the slip line method. Okay, they have not discussed the slip line method, but they have given how to draw the slip line for our specific case. That is for this geocell design, how to draw the slip lines. They've given the direction and how to calculate everything. They have given all the instructions there. Okay, so I suggest that you go through this. And if you want to understand what is slip line method, I will suggest that you study some literature or some books on this plastic equilibrium soil that they are deals with the limit analysis and all those things. There we will get this slip line method or method of stress characteristics to interest a slip line. So in a simple way, there is nothing but a numerical technique where you can get the slip lines or the failure lines or the failure surfaces, and using this technique, you can get the numerical technique, can get the stress at any point in the continuum, soil continuum. All right. Now, so in this design, the plastic bearing of the soil possesses instead of slip circle failure. So generally what we do, generally we assume a slip circle failure. And what is this slip circle failure? This slip circle failure is nothing but a limit equilibrium technique. Okay. In limit equilibrium technique, this what we said, what we assume is that in the slip circle, the soil is about to fail, right? This is about to fail, and uh, about to fail. And so what we do, we equate the oncoming stresses and the resisting stress. So we assume that the complete uh, stresses are mobilized. But this is a plastic, in this a plastic bearing of the soil. So when the soil goes into the plastic state, okay, the soil is not in elastic state. It's completely in a plastic state. Okay, in that plastic state, in that plastic equilibrium condition, we use that equilibrium condition to determine the stresses. All right, so that's this is the concept of slip line. From there, we finally mathematically we derive the slip line. Let's okay. So this type of failure, so the failure for which we will be designing this geocell in our specific case, it's only specific to the case where the width of the embankment is more than 4 times the depth of the foundation. So, all right. So we have a foundations, have an embankment on a foundation side, and here we have the strong base. So this depth D of the soft foundation soil should be more than 4 times the width of this amount. The soft soil, so we can, as you can see, this soft soil is sandwiched between our embankment and the what and the hard strata at the bottom, isn't it? This soft soil is sandwiched between the embankment and the hard strata at the bottom. Okay, so if some is soft, something is so this so some researchers had actually given some theories where they uh, gave so where they showed how to solve such problems where we have some soft strata between two strong objects, right? it's a soft metal between strong metal. Right. So using that analogy, this non-symmetric strip line is constructed in this soft soil. Okay. So what happens is that uh, this plastic surface actually move inwards. Okay. So how to say? So see, here we have the embankment, right? And here we have the strong. So this here you have the soft side. So what happens? So this surface is a rough, right? So the plastic surfaces actually come inwards. Okay, come inwards. Okay, the plastic surfaces they start to develop inwards. Okay, from both directions. Okay, in the soft side. So that concept is actually used to develop a non-symmetric slip line. All right, and using that slip line, we actually determine the stress at each point. Stress or the stress coming at each point, and using that, we actually design the final this geoset. We select the geoset. Actually. Okay, we select the geoset. Here is here selection is a better word. Okay. Okay. Now, a 15-degree slip line field was used to determine the bearing distance of the soil. So, slip line, if you go into details in the slip line method, you will see what. So, now actually it won't be clear to you, all right, because you don't know what is slip line method, better of stress characteristics, how the slip lines are coming, how it is drawn. So, you don't know. So, slip line just use for now, just to know that these are just failure lines along which this plastic force, this soil will fail. And these slip lines are we are drawing the slip line at 15-degree intervals. Okay, at every 15 degrees we are drawing them. In this case, in this 15 degree was actually chosen by them, Jenner. Okay, Jenner et al. Actually chose 15-degree to. So that is they might be having some reason for that. For that, you have to go through their paper in detail. So they decided that they will choose 15-degree slip lines. Okay, so as it is written here, the construction of slip line field and corresponding bearing pressure diagram are discussed in detail by generator. So how to get the bearing pressure diagram? Those steps are actually discussed in the paper. So I will suggest that you go through. A typical bearing capacity diagram for the geocell supported embankment drawn based on the slip line field is shown in the figure. So you can see we have the embankment at the top, right? So at the top, and we have put a geocell layer at the bottom of the embankment so that the embankment can rest over the geocell layer. Okay, so it can provide the stiffness. So this geocell layer will actually be acting as a foundation, strong foundation. Right, for the embankment, it will be acting as a strong foundation. This geocell layer. All right. Okay. So you can see here we have the embankment, you have the geocell layer. Now, using this slip line theory, what we do is we try to draw this pressure diagram. So we have an embankment. So the embankment is symmetric. So at the center line, we take one half of it. We take one half of it. It is symmetric thing, right? So we take the plane of symmetry. This is the center. This is the center line. Just we consider one half. Now at the edge, just here we consider that the bearing capacity is nothing but 5.71 CU. Okay, because it is little more than the plastic limit. Okay. 5.71 CU. Okay, we considered this is the elastic limit. We considered this. Okay, we considered this at the leftmost edge, and this so in say if x and y, so in y direction, in this direction we have this bearing capacity. Okay, in this direction. So from here to here, we have 5.71 as the constant bearing capacity. 5.71 CU as the constant bearing capacity. Okay, all these are given by general. From here to a distance of D, where what is D? D is the depth of our soft soil or the soft foundation layer. Okay, D is the depth of the soft foundation layer. Okay, of the soft soil layer. Is that depth. So up to that so up to D width, up to D portion, what we have in this direction up to D length, we have 5.71 CU as constant. Okay, it's constant bearing capacity. Now, for the rest of the portion, we need to determine. From here to here, from here to here, all these bearing capacities, bearing pressures, we use the slip line theory to determine this. All right. And from from this part onwards, from here to here, actually, okay, from here to here, actually, this we consider this portion as the rigid head. Is the rigid head? We will see that in the next slide. From here to here, we consider that this is the rigid head. Okay, and a formula was given, an expression was given to calculate the average pressure across this rigid head. So if you know the pressure at this point using the slip line method, you can get this average pressure using the expression given by generator. All right. The bearing capacity diagram was developed from the outer edge of the slip line fields towards the inwards to the boundary of the rigid head, defined on the slip line field by ratio of geocell width to depth on the soil. Okay, so the bearing capacity diagram was developed by working from the outer edge of the slip line field to the from this outer edge to here. Okay, the rigid head is the term used by Jenner to denote the soil zone which does not experience plastic streams. Okay, the rigid head, which is the center. Okay, so here taking the symmetry, right? So rigid head will come at the center of them. At how much? At one, this portion from here to here, we have the rigid head, 1.25 D, that length, that width. Okay, we have the rigid head. So what is rigid head? Rigid head is where the soil does not experience plastic streams. Okay, the soil does not experience plastic streams. Right. Thus, the slip line field is used to define the maximum allowable pressure distribution within a zone of limiting plasticity. All right. So 5.71 CU. What is 5.71 CU? What is 5.71 CU? 5.71 CU is our elastic limit. So below 5.71 CU, it's what? It's what? It's plastic. It's plastic, right? So below means what? Below means, say, if the bearing pressure of that place is less than 5.71 CU, that means what? That means when load will come, the soil there will be uh, in plastic state. Okay, but now what we are doing as we go in this direction, what is happening? That limit is elastic limit is getting increased. It means it can take higher loads till which the soil will remain elastic and not go into plastic state. All right, the limit is going increasing in somewhat sense. All right, okay, you can think it in that way that the limit is increasing. Initially, what is the normal soil? For normal soil, what is the elastic limit? What is the elastic limit? It's 5.71 CU. This is the elastic limit for a normal unreinforced soil. But due to the reinforcement, what is happening? Our elastic limit is increasing. That means it can take more load. The soil can now take more load without going into plastic state. Okay. Okay. Now the tensile forces. The tensile force forces in the mattress are the mattress here means the geocell. The tensile forces in the mattress are determined from the stresses acting on the base of the mattress. Understood? So in the geocell, there will be some tensile forces that will be acting, right, due to the load that is acting on it. So that tensile forces are determined by determining the pressure or the stress at the base of this geocell layer. Okay, at this level, at this place. So that is what we need to determine using these pressure diagrams. Okay, the tensile forces in the mattress are determined from the stresses acting on the base of the mattress. The stress distribution across the rigid head can be determined by considering the rotations of each of the chords of the stress field bounding the rigid field. Okay, the average stress across the rigid head can be determined by considering the rotations of each of the chords that actually bound that rigid head. Okay, now the average pressure across the rigid head can be calculated as this. This was given by Jenner. P dash by Cu is equal to 2 of 2 psi plus 0.5 T by 2 s plus P by C. What is P by Cu? P by Cu is the value read from the stress field at the extreme end of the rigid head. Means where is the extreme end? This point. Okay, at this point. This is the extreme end of the rigid head. That P by Cu is the pressure here that we're reading from this pressure diagram. Okay, here this is the extreme. That plus some other factors will give you the average stress over that. All right. For designing the geocell mattress, consider an element of soil within the geocell cellular mattress, but interfacing with the soil layer, with a soft soil. So we just consider an element of soil within the geocell mattress. Soil, the geocells are cells, right? So within the cells of the geocell, we'll be having soil. That soil also will have interface with the soft soil layer, right? We'll have it will have an interface. We will be touching the soft soil. The horizontal stress on the element is given by this equation. Sigma h is equal to sigma n minus twice x. And what is x? What is sigma n? Sigma n is the vertical stress on that element. It is the overburden pressure on that element, on each element. Okay. And what is x? X is given by this expression. Okay. And you can see this x depends on the normal, the vertical stress. The phi is this phi dash. This phi dash is the phi of the soil that is filled in the geocell. Okay, that is that. All right, it is that phi. And it also depends on this tau value. And what is this tau value? Tau is nothing but the shear stress at the interface. What is the shear stress? Cu in the limiting condition. We'll see that. What is Cu in the limiting condition? The rotation of principal stress occur within the mattress tab. Okay. Therefore, a geocell mattress, this is important. Therefore, a geocell mattress having tensile strength equal to the expected horizontal stress should be used to support the embankment. So we will be calculating the vertical stress. Okay, we're calculating the vertical stress, and we will be saying that the geocell greater than this tensile strength of this vertical stress, the horizontal stress should be active. We will have to use. Okay, geocell metals having tensile strength equal to say you get at this sigma h is equal to 50 kilonewton per meter square. That means we have to use a geocell of 1 meter height having tensile strength greater than 50 kilonewton per meter. Okay, in simple words. Okay, say you get this horizontal stress sigma h. This horizontal stress ultimately comes out as 50 kilonewton per meter square. That means you have to use a geocell mattress of 1 meter height having geocell mattress 1 meter thick having a tensile strength equal to 50 kilonewton per meter. Greater than or equal to 50 Newton per meter. All right. So all this that I had discussed is Everything is described in this paper by G. Madhavi ma'am from ISA Bangalore. So she had actually done a research on this. And if you go in this paper, you will see that many other methods are also summarized. Okay, one method is given by her itself, and some other methods are also there. All of these methods, method is also given by Professor Rajagopal sir. So all these methods are actually summarized. So what I suggest is that you go through this. This is a very short paper, just in simple words, everything is summarized in this. Okay. So what I suggest is that you just go through this paper once. All right. This was the problem that was given in the handout. So actually, how the solution was given in this, actually that is not clear to me also in detail. So just still let us just see what they have tried to do here. Okay. Okay. This is the question that is given in the course handout. Okay. In your course handout. So some parts are not even clear to me how it is. Still, let us just see. So, we design an embankment resting on a thin layer of soft soil and supported by geocell mattress. The height of the embankment is 6 meters. Okay, so height of the embankment is 6 meters. The thickness of the soft soil layer is 4. Okay, so okay, obviously you can see 4 times 4 is 16. So the width of the embankment is obviously larger than 4 times the depth of the subsoil layer, thickness of the subsoil layer. So this whatever theory we have discussed just now, we can apply that theory. Right? So design an embankment resting on a thin layer of soft soil and supported by geosoil mattress. The height of the embankment is 6 meters and the thickness of the subsoil layer is 4 meters. Embankment has a slope of 1 vertical to horizontal. The top width of the embankment is 36 meters. Geocell mattress has a thickness of 1 meter. Okay. The embankment is a surcharge of 20 kPa, and the unit weight of the field is 18 kN per meter. Just a second. Yeah. So what we do, we consider, so this is the embankment, as you can see. Yeah, this is the embankment. So, uh, excuse me. So half portion of the embankment is total was 36 meters, so 18 meters. So half is taken. All right. And after taking that at 15 degree, so the slip lines are 15 degrees, slip lines are constructed. Okay, all these are 15 degrees. So various softwares are also available by available, right? Tensor and all. So those can be easily used to construct these slip lines. Now you can see, so here from here we have 1.25D. Okay, we have 1.25D, 5 meter. This gives us the rigid. This part gives us the rigid portion, right? Okay, the rigid portion, and this is the chord that separates the rigid portion. All right. Now from the above slip line field, G3H1 is alpha line along which P plus 2ICU theta is constant. This is actually this angles. Okay, these angles, how much rotation each slip line is taking. Okay, these angles. From G3 to H is a negative rotation of 15 degrees. 15 degrees means 0.262 radians. So along G3H1, it's along this line, this alpha line. G3H1, what is PH1? The stress at, so here we know at G3, at G3 point, it is at distance D. So if you want to look again, so up to D distance, this is 5.71 CU. So we are drawing the slip lines from here, right? And from this point. So at this point, at D distance, you can see at D, at here, at G3, at G3 point, what is our pressure? 5.71 CU. Right. Now, if we want to go from G3 to H1, what we need to do? We need to add twice CU theta with that. Okay, then we will get the pressure at H1. Okay, this is how actually the slip line method works. So you know from one portion we know at one point we know the stress or the pressure. Using the slip line, you can calculate the from one to other like that, from one to one like this. We can calculate the pressure at all points. Okay, like a network thing. From one to one like this, we can calculate. To this G3 you are adding with this much, that will give us the H1, pressure at H1. So pressure at H1 is 5.71 Cu plus 2I Cu theta. So Cu theta will get 6.234 Cu. So at H1 point, we have 6.234 Cu. Okay. Now we need to get at the H, right? So H1 is a little bit below. H is here along this, what to say, this beta line. Okay, this is the beta line, this is the alpha line. So this beta line, you have to go up to H. Okay, to H. So here again we have to take one more rotation. So we have P at H is equal to PH1 plus 2I Cu theta again. So this 6.234 Cu plus 2 into Cu into this 0.262. Again 15-degree rotation. So again, so we will get finally at H you are getting 6.785. So here this is this, like H you will get some value here, which is nothing but 6.785. So like this, what you have to do, you have to find the pressures at all these points. Okay, one by one. Like the network way you have to go. You need to find the pressure at all these points. All right. Now, like this, so finally, after finally we reach here, PD at D point. Finally, after finding all this, we reach this D point. So here they have determined the stress at this D point here. Okay, you find the stress at this D point. Okay, here I do not understand actually what they did. This 10 I understand. 10 is actually, see, 10 jumps are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 from here to here, 10. And this 2.62, I understand the rotations, but actually it is not clear to me how they took this 4. All right, so if I understand, I will let you know, but this is not actually clear to me. So actually what they might have done is that this 4 is this depth, this height, right? This total thickness. From here to here in 15-degree rotation, they have done something. From G3, say we have an arc like something they have done. From G3, we have to reach D one by one. So it's better to calculate slowly, gradually, then reach D. So what they've done, directly calculated at this D point. Okay. What they have done is G3, they have added 10 times, I understand. This is 10 jumps times 4 they have done. 4, I think this, the 4 they have done for this depth, height, times twice. So this is not clear. Well, leave it. So finally at D point, we get the stress as this much, 60.19 CU. Okay. Now at D point we got, now we can get the average at, in this rigid portion. Okay. In the rigid head we can go. So at this point we have got, okay, which is 16.19. Now to get this average stress, we have to use this expression given by Z. Okay. Now the rigid head is at least this was 1.25D. So this one, this is the rigid head. So now what they have done, they have used this expression. So this was 16.19, right? So this they have added. So they have taken all these R chord lengths, all this AP, VCCT, all these chord lengths, then this rotation, how much rotation each chord is taking, all these things. They have taken the product, I product. So total I they've got, this X they have got. So finally put in the expression to get the P dash by CU is 17.26. This much is 17.26. All right. Now, assuming 1 meter length means length in this direction, the out of plane direction, length means out of plane direction. The load from half of the embankment includes the including the surcharge. So here nothing, just the total load. So the weight of the embankment plus that surcharge. Okay, this thing there here. So so we get 2952 Newton per meter as the total weight of the. Okay. Now the resistance that is coming from the geocell, how to get that from the pressure? We will get from this bearing pressure diagram. Okay. If we take the area of this bearing pressure diagram, we'll get this. Now Cu required to prevent plastic deformation is nothing but how much? Cu should be how much to prevent plastic deformation? This divided by this. So at least we need to have 9.31 Cu. The cohesion of the soft soil should at least be 9.31 in order to uh, prevent the plastic deformation of the soil. Right. All right. So in order to resist this load, at least the soil should have 9.31. Now, in that case, what is the factor of safety? Will be equal to 10 by 9.31 is 1.0074. Okay. So if we want the factor of safety to be 1.5, the CU should be at least 15 kp. CU of our soil should be at least 15 kp. All right. So in this soil, actually, it won't work. For that, the CU of the soil should be at least 15 kp. Okay. The rest of the problem is solved thinking that uh, this one, CU is 15 kp. CU of the soil is 15 kpa. So at least the CU of the soil should be 15 kpa in order to get a better safety of 1.5. Right? Now this CU that we got here, 9.31, this CU is nothing but the limiting CU. Okay, this limiting. This limiting CU. This they have actually done wrong. Okay. You just do this by yourself. This CU, this is the CU limiting. So if you want, you just see that paper by Professor Madhavi that I just discussed in the previous slide. There also one example has similar example has been shown there. I suggest that you go through that example once. Okay, please go through that example once. So for electricity 1.5, you should be 15 kPa. Now our next task is to determine the horizontal stress within the geocell. So as we discussed, this is the expression we need to use. So what is the vertical stress is coming? Gamma into h plus surcharge. So gamma into 6 is the height. The surcharge 128 kPa. Now you need to determine this x from here. Okay. So this tau here the tau should be how much? This 9.31. Okay. So put 9.31 and find this x. Whatever x this comes here, x this comes here. From that x, we find this sigma h by using this expression. Okay. So sigma n minus 2 times this x will give you sigma. So as we had discussed, the tensile strength should be greater than this value. All right. Tensile strength. So here it is 52 kP. So tensile strength should be at least 52 kilonewton per meter. That's yourself. All right. So again, I will suggest that you please go through that paper which I had mentioned. So in that clearly everything is written. Okay. Yeah. So yeah. So now let us come to the next part of the video. So this portion, this is not this is extra topic that I'm discussing. As we have around 40, 45 minutes, 45, 50 minutes, 45 minutes of time. So let us just, I thought that I will just discuss this thing, this topic. This topic has not been as per my knowledge. This has not been discussed in the class. So just for your knowledge, okay. This is, if this is not discussed in the class, this also won't be included for the exam. All right. This is the extra topic. So if it is, if it has not been taught in the class, it won't be there in the exams also. All right, extra topic from my side, from my side for your information, I am giving this. As we have time, as we have some extra time, just for your knowledge, I am just discussing this. All right. So if this has not been discussed in the class, so as per my knowledge, it has not been discussed in the class. So if this topic has not been taught in the class, this won't be in coming in the exam also. All right. So just for your information, just for your knowledge, I am discussing this. Okay. Okay, just you can just go through it lightly, just so that you just so that you know what what this kind of thing also exists. Okay, just for your knowledge. Unpaved road. Okay, geotextile for reinforcement of unpaved road. So what are unpaved roads actually? When I say unpaved roads, what are unpaved roads? So soft soil subgrades that have sand or stone aggregates placed directly above it. So there is no pavement like black topping or some bitumen layer or some asphalt layer. Nothing is there. Okay, directly soft soils above the soft soil subgrade. Above a subgrade, what we are doing? We are providing this sand or stone aggregates. Okay. No permanent surfacing such as concrete or asphalt pavement is not placed. Okay, not. It should be not placed. Okay, permanent surfacing such as not placed. Okay, permanent surfacing such as concrete or asphalt pavement is immediately not placed. All right. Road may be surfaced with quarry crusher run or cheap seal for result. So just so that we have uh, reasonable rideability, just so that the vehicles will move easily. What we do, we just place crusher stone or chip to just have a little bit of smooth surface. Right? So at later time when settlements have taken place and the ruts that have occurred in the movement of the vehicle have been backfilled, the permanent surfacing may be placed. Okay, that may be placed in the future. But in the present case, what we are doing, what we have an unpaved road that has to be made service. All right. So let us see how this geotextile and geography actually help in this reinforcement of unpaved. Okay. So again, I would like to mention that this is an extra topic. So as it is an extra topic, we're discussing only because we have some time with us. We have a lot of time with us. So just I thought that just for your information, I will just share this with you. Just for your knowledge, just you should know this thing also. I felt that this is so if this is not taught in the class, in the main lectures, this won't be included in the exam also, obviously. All right. So just for your knowledge, I am discussing this thing. All right. So researchers Giraud and Noire actually use this geometric model which is shown here. Okay, shown here. So to analytically give the solution for this problem. So in the left side, you can see if we do not use geotextile, we need to use we need to have a depth of this stone filling or sand filling, aggregate filling. Okay, granular soil filling of depth h naught. Okay, but if you are using geotextile, this height of filling reduces. This height of filling is reduced. So below we have a separate soil. Okay, so we need to place some aggregate layers above it so that the so that the stress coming the load coming on the subgrade soil is sufficiently reduced, sufficiently spread out, sufficiently reduced or spread out. Okay. All right. So without geotextile, we need to use H naught height. But if we use geotextile, what will happen is that the, the aggregates that we have to use to construct the unpaved road, that aggregate has to uh, depth will reduce from H naught to H. So in that way, we will be saving cost, obviously. Obviously, if we reduce this height, we will be saving huge costs. Say if to construct 2 kilometer road. So overall, if you are overall, if you are this reducing this height, then you will be saving a lot of cost, isn't it? A lot of cost will be reduced. Okay, so that is our task, that to use geotextile or geogrid so that you can reduce the cost. So you can see here. So PEC is nothing but the pressure that is coming from the tire of the vehicle. Okay, pressure that is coming from the tire of the vehicles. Okay, this PEC is that pressure is coming from the tire of the vehicles. That PEC pressure is obviously spread out. Okay, this at an angle alpha naught. This alpha naught is generally taken tan inverse of 1 by 2. Generally, say 26 degrees, approximately 26 degrees generally taken. Okay, so the PC spread out to P naught. Okay, as it goes spread out, this reduces to P naught. All right, and similarly, when we're using geotextile, that will also happen. Same thing will happen. So this gamma into H naught you can see is nothing but the what? This gamma into H naught is the overburden pressure. Okay, this gamma into H naught is the overburden pressure of the soil, and this here at this portion, this P naught is acting. This P naught includes the overburden pressure and the pressure that is coming from the wheel loads. Okay, so this P naught is the pressure that includes the overburden pressure gamma into H time and the pressure that is coming through the wheel. When we're using the geotextile, this height is going to get reduced. So obviously, this overburden pressure will also reduce from H into gamma into H naught to gamma into H. Okay, and here this dispersion is actually at an angle of alpha. So actually, this alpha angle is not equal to alpha naught. The dispersion angle, this alpha angle is actually not equal to alpha naught. It in reality, it actually comes out to be a little bit larger. Okay, but we will solve one problem initially where we will be taking this alpha equal to alpha naught just for the solution purposes. Okay, for the initial solution. Okay, but generally, practically, what happens is alpha, this angle, dispersion angle actually becomes higher when we use geotextile or any other inputs. Okay, now this P naught, here we have P naught, here we have P. So let me write down the expressions for both P naught and P. So P naught is actually given by P by H naught. So this is nothing but the area, right? So this area, this time this area, it's length into breadth. Okay, length into breadth, length into breadth. Okay, length into breadth. This length into breadth is what? Tire contact area. This area is getting expanded here below. So that expanded area is nothing but this. All right. And P, this P, this P here, when we are using some reinforcement, is same, but here it's H. Okay. What is P? What is this capital P? This capital P is the axle load. Okay. This capital P is nothing but the axle load from the vehicle. Okay. And what is gamma? Gamma is the unit weight of the stone aggregate. Okay. Capital P is what? Capital P is the axle load. Now, now what happens? What happens is that it is assumed uh, that in the first case, when we are not using any reinforcement, the soil reaches its elastic limit. Okay, the elastic limit. The soil reaches its elastic. This is what we assume. Okay, so we equate P naught to what is the elastic limit of the soil? Plus gamma into H naught. Okay, but when we are using reinforcement, when we are using the reinforcement, this limit actually gets increased. This limit actually, let me not use this. So when we are using reinforcement, this gets increased to 5 plus 2C plus gamma H. Okay. So these are the assumptions that have been made by Giraud and Noir. All right. So let us mark this is equation 1, equation 2. Now what we can do? We can equate equation 1 to this expression. This you can equate to P naught, and this we can equate to this P. Okay, so let us mark this 3 and 4. So from equation 1 and 3, we get, we equate these two equations, we can get the cohesion C as P by 2i pi root over P by PC plus 2H naught 10 alpha naught again root over P by 2i PC plus 2i H naught 10 alpha naught. Okay, so using this expression, if you know the cohesion, if you know if you know the cohesion, if you know P, you can, if you know PC, if you know alpha naught, what we can get? We can get the height of the aggregate that we need to use. This is the unreinforced case. There is the H naught case. So C is what? So I will just define the terms here. Just a second. I will just add some more pages. Okay, just a second. Just give me a moment. All right. All right. So let us define the terms. What is C? C is the cohesion of soil. What is capital P? Axle load. What is PC? PC is the tire inflation pressure. Okay, the pressure at which vehicle tires has been inflated. Okay, what is H naught? Aggregate thickness, alpha naught angle of load distribution, approximately 26 degrees. Okay, now this this was the, just a second. Now, for the case where we are using geotextile reinforcement, okay, for the case where we are using geotextile reinforcement, for the case where geotextile reinforcement is used, equate equation 2 to P minus PG. Okay, means equation 2, equation 3, sorry, equation 3 to P, not equation 4 to P minus. I will show you. So we will have, what was the equation? What was equation this one? If this, what was P? P was this, right? From equation 2. This was P. The P minus PG. What is PG? I will tell you. So P minus PG, P minus PG is to be equated with equation 4. And what was equation 4? Pi plus 2C C plus gamma into H. Now what is PG? PG is E into I A plus A by 2x square. Okay, so E, let us define the terms here. E is modulus of geotextile. What is E? Elongation. All right. What is A? Geometric property. What is S? S is the settlement under the wheel. Okay. Now, if you do all the stuff, if you all the equating, you will get the final expression as this. Okay, this is the final expression. So from this expression, our task is to get H. Okay, so what are the equations? What are the main equations, final equations? So this is one equation. This is one equation. And this is one. Okay, so these are the equations that we need to use. All right. So you will see that is H that we determine it will be less than H naught. So Giroud and Noire were also given some curves. From this equation, what they did was for particular wheel load and this tire inflation pressure, they constructed some curves like this. This. So for wheel load of say XL load of 80 kilonewton, rating settlement of 0.3 meter, and this inflation pressure of 480 kPa, they constructed this curve. So similarly, you can construct for several wheel loads, you can construct similar curves corresponding to number of passes, elongation of the geotextile, okay, and the modulus of geotextile. And from here, you can get the H naught value and the delta H value. And the H value is nothing but H naught minus delta H. Okay, from the curve. So first, let us just also relating to the CBR also. Do not forget CU and CBR. So first, let us analytically try to solve one problem, and then from this graph we will see how. From this graph we will see how to get. So given 340 passes of 80 kilonewton single axle load vehicles with tire inflation pressure of 480 kPa, soft soil CBR is equal to 1, CU is 30 kPa, geotextile modulus is given, rad depth is given 0.3 meter. What is the required aggregate thickness of unpaved road? Okay, that means H not we need to determine first. Okay, so let us just find it. Very simple, 30, sorry, 30 is equal to 80 by twice by